Welcome back to Kotlin at Lightspeed. This is Daniel, and in this part, we're going to talk about object-oriented programming in Kotlin. We're going to continue with the project that we made over the past couple of videos. So if you haven't done so already, I recommend that you check out the first video in the Kotlin at Lightspeed mini-series, in which I describe what the Kotlin language is and why we write it, as well as the development environment and the software and tools that you need to get started. In the previous part, we ran through the basics of Kotlin, including values, variables, types, type inference, regular types, strings, instructions, expressions, and looping in Kotlin. So if you haven't checked out that part, I recommend that you do that now before we continue. In this video, we're going to go through the object-oriented features of Kotlin. So under the Rock the JVM package of the Kotlin at Lightspeed project, I'm going to create a new standalone application. I'm going to call this OP, and I make a standalone application so that we have the code nice and clean. All right. Cool. So I'm going to type in a main so that this becomes a standalone application. And in this video, I'm going to describe every bit of syntax here. So this is a standalone application. Right now, this application doesn't do anything. We don't even have a print line. And at this point, we should be ready to get started. Now, in Kotlin, we can define our own data types in the form of classes. So if you've seen any other object-oriented programming language, for example, Java or C# or TypeScript or things of that sort, we have the same concept of classes as we have in those languages as well. So let me define a class. I'm going to call this pet. And let's assume that this pet has some, we call them properties, that is pieces of data associated to pets. In this case, I'm going to define a val called age, which let's assume is equal to 0. And we can define functions. And this is a piece of behavior. And functions can be defined with the same syntax that we described in the previous video. For example, let's assume that this pet has a function to eat something, so eat. And let's assume that the implementation of eat is print line, I'm eating something, assuming that they could talk. So class describes a concept in real life, and we model that in programming in terms of properties as pieces of data, and you can define as many properties as you like, and in terms of behavior in the form of functions. We call them methods in OOP, or in the context of classes. So methods are pieces of behavior and properties are pieces of data, and you can define as many of them as you want. Now, in order for us to actually use instances or concrete allocations of memory that conform to the structure, we say that we define a val, let's call this a pet, as pet invoked like this, like a function. We say that this pet value has the type called pet. And once we have an instance, it's called, so this is an instance of pet, or an allocation of memory that conforms to the structure defined by the class. Now in main, you can say a pet dot, and then we can say eat. So we can invoke the method eat on the pet instance that we just created. So in this case, we're going to see I'm eating something because that's what the function does. Okay. Now, this is called an instance of pet, and the act of invoking the name of the class with some arguments is said to be the instantiation, or the construction of an instance of pet. Now, currently, the pet constructor, or the pet class definition, doesn't have any arguments, which is why we call the pet constructor with no arguments. But there are classes where we can define classes with constructor arguments, as I'm going to show you shortly. At the same time, I'm going to show you how you can create relationships between the concepts defined by classes in the form of inheritance. Inheritance is something specific to OOP, or object-oriented programming, and you may have seen inheritance in other languages as well. The Kotlin language is no exception. So I'm going to define a class dog, and let's assume that this dog class has a name as a string. So notice that once I'm defining the class dog also with some arguments, these are the constructor arguments of the class dog. So if I define a val, a dog, as dog with the name Lassie, this is a proper instantiation of the dog class. Okay, so once you have constructor arguments, naturally you have to pass some constructor arguments when you instantiate this class. Okay, cool. So that's with constructor arguments. Now, I want this dog to be related to the pet class in the sense that dog is a subtype of pet, which makes sense in the real life. Dog is a kind of pet. So we say that in Kotlin, this extends the pet class, and the syntax for that is to say the class dog, and after you mention the constructor arguments, derives from or inherits from the pet class with no constructor arguments. So you have to provide constructor arguments for the type that you want to inherit from. Now I'm going to open some curly braces, and in order for me to inherit, that is, take the properties and functions from the pet class and have them accessible in the dog class, I'm going to make the class open. By default, classes are not extensible unless we add the open keyword to them. So when we build the class dog, we're actually building a pet, and then we add some additional properties, methods, and so on. For example, now that a dog is a subtype of pet, I can also call the eat method from the pet class. So I can say a dog.eat. So once the dog type is a subtype of pet, I can access all the properties and methods of the parent class. In this case, this application will print I'm eating something twice. Now, I'm going to stop at this point and add a couple of clarifications. For example, the class dog has a name string as a constructor argument. That is not the same as a property of the dog type. For example, I can say val dog name as a dog. You may be tempted to say .name, but this is not actually legal, so it's not okay. That is because the name that you pass in as an argument cannot really be accessed as a property. So constructor args are not properties. If you want to make them properties, you have to prefix them with the keyword val or var. After I prefix the constructor argument with the keyword val, this is actually saved inside the class dog under the name, obviously the way that you named the constructor argument. So the lesson is that constructor arguments are not properties unless prefixed with val or var. That's one lesson. The second lesson is that once you open the door to inheritance, the question is, can you change the behavior of one of the methods in the parent class? That is, can you override the behavior of the parent class? And in most object-oriented programming languages, you can override them in various ways. I'm going to show you the way that you can do that in Kotlin. First of all, you have to make the method that you want to change with the keyword open. So you want to prefix the method with the keyword open, meaning that this method can be changed or overridden in child classes. Meaning that you can provide another implementation for the eat method by saying override fun eat with the exact same signature. So override fun eat with the exact argument list, in this case, no arguments, and returning the same thing, in this case, the type unit. Obviously, it doesn't return any meaningful value, so the return type of this method is unit. So I'm going to say print line, I'm chewing something, what you're looking at. Well, now in this case, if we run the same application when we say a dog.eat, the behavior is going to be picked from the overridden method, not from the parent class, because now the eat method has a different implementation. So if we run this application, we're going to see first, I'm eating something from the first animal, so the first pet, and the dog.eat now has a different behavior, saying I'm chewing something, what you're looking at. So you can change behavior from the parent class. That's called overriding. Now, this concept is very familiar to those of you who have done any sort of object-oriented programming in other languages, for example, in Java or in C#. This concept is also present there. Speaking of inheritance, we also have a concept called subtype polymorphism. Now, this sounds a little psychobabble, but what this means is that you can define a value, let's call this my pet, which is known to be of type pet. So I am specifying the type here manually and explicitly because I want to show you something. And on the right-hand side, I'm going to pass an expression that is a proper substitute or a proper subtype of pet. For example, a dog. So I'm going to say dog with Hachi. Hachiko is one of my favorite movies with pets of all time. And this dog Hachi is an instance of dog, naturally, but because dog is a subtype of pet, the expression dog hachi is a proper substitute for the type that I'm expecting here. In this case, once I say val my pet is equal to dog hachi, then I can use the methods from the pet class. So for example, I can say myPet.eat. But in this case, the eat method will be called from the most derived type, so from the actual instance of myPet at runtime. So the eat method from dog will be called at runtime. So the compiler knows that the eat method is available on this variable because it has the type pet, and therefore, because the type pet has the eat method defined there, the compiler knows to call this method. But the behavior from the eat method will be called from the class dog, the actual instance that I'm using here at runtime. So this is very, very important, but I'm pretty sure you know this from other languages. So we have the concept of subtype polymorphism here in Kotlin as well. Okay, so this thing is very important, this part: classes, instances, properties, methods, inheritance, and overriding. Now, once the door opens to inheritance, we have a bunch of additional concepts. For example, we have the concept of an abstract class in Kotlin. An abstract class is a class for which you can define methods without implementations. So let me show you. I'm going to say abstract class. I'm going to call this walking pet. Walking pet. Obviously, there are various kinds of pets. Maybe they're snakes, or they're flying pets, or they're walking pets. Let's assume that we are dealing with walking pets for now. And we have a val has legs is equal to true as a property. And let's assume that we have a method called walk, which is different for every walking pet. Maybe cats and dogs walk differently, and so on and so forth. So I'm going to define a fun walk that returns unit. So I have to specify the type here, but given that there's no general walking style for all walking pets, assuming that this were true, and leaving the implementation or the behavior to the class in question, for example, dogs and cats and whatever, I'm going to mark this function abstract, meaning that I'm not compelled to leave any sort of implementation. So may not necessarily have an implementation. This structure is called an abstract method, and a class that has abstract methods or can have abstract methods is called an abstract class. Abstract classes have some restrictions. For example, they cannot be instantiated on their own because they don't have all their behaviors defined and so on and so forth. But in general, the concept of an abstract class involves the capability of defining methods with no implementations. And the natural extension to that is the ultimate abstract type, which has no methods with any sort of implementation, and that is called an interface. You may know this concept, for example, from Java. The interface is the ultimate abstract type, and the keyword for that is interface. For example, interface carnivore. And interfaces generally describe traits in real life. For example, the ability to eat meat or eat other animals. So I'm going to say fun eat animal that is of type pet. So a carnivore can eat your pets, for example, an alligator or something like that, and this returns unit. Now, in interfaces, you don't really have to define methods that are abstract because the abstract keyword is implied. So every single method that you define in interfaces is assumed to already be abstract, so you don't have to define the keyword abstract for every single method. Okay, let me define an interface called cold-blooded. And I'm going to define some types that derive from these abstract things. Now, the inheritance model in Kotlin, so the inheritance model, is that any class with definitive behavior, so a class, can inherit from one class and potentially more than 0 interfaces, meaning multiple interfaces. Let me define a class, snake, which derives from pet. So some people have snakes as pets, like pythons and things of that sort. So class snake extends pet and also carnivore and also cold-blooded. So this is how you specify the types that you inherit from. First, you specify the class that you're inheriting from, and then all the interfaces one by one. Now, because this class snake is not abstract, and because carnivore, for example, has an abstract method, the compiler doesn't allow us to define the class snake until we either make it abstract, which allows it to keep the eat method without any implementation, or compels us to provide an implementation for the fun eat. So I'm going to have my override fun eat, and IntelliJ is smart enough to auto-suggest that for me. And I'm going to say print line I'm swallowing this poor sucker. And otherwise, you can have additional properties, methods, and overrides from other parent types. For example, I can override the eat method from the pet class, just like we did before on the class dog. So this is the inheritance model from Kotlin in one line. One class can inherit from at most one class and potentially multiple interfaces, as we see in this example. And otherwise, Kotlin has many of the similar features to other languages. We have access modifiers like protected, private, and things of that sort. We have overloading, meaning that we can define multiple methods with different signatures or different argument lists in the same class, and so on and so forth. Now, specific to Kotlin, and this was inspired by other languages like Scala, but the concept is, at least in this form, unique to Kotlin, is objects and companions. Now, the keyword object has a special meaning in Kotlin. This was inspired from the Scala programming language. And if I define an object with a keyword object, and I'm going to call this my object, we essentially implement what is called the Singleton pattern in one line of code. Now, those of you coming from object-oriented backgrounds may know the Singleton pattern as quite a delicate design pattern in which we force a type to contain at most one instance of that type, and that's useful for a variety of scenarios. In Kotlin, when we define an object, we define a type plus the only instance of that type in one definition. So for example, here I've defined the type, my object, as well as the only possible instance of this particular type. For that reason, I'm going to call this my singleton. Okay, now once you define an object, my singleton, you can open some curly braces, and just like a class, you can define properties and methods. For example, val a property is equal to 42, and fun a method that takes an arg as an int, and this returns an int. And here I'm going to say print line saying hi, hello from singleton, and then I'm going to use the arg just to use this parameter and return a property plus the arg. So you can define properties and methods inside objects like you would on regular classes. Now, the way that you would use these properties and methods, for example, here in main, I'm going to say print line. I'm going to say my singleton. So I'm going to refer to the object itself, like I would on any other variable, dot a property. And obviously this will print 42. And you can also call a method. So I'm going to say print line my singleton dot a method on the argument 78 or something like that. So a method will obviously print hello from singleton with the number 78, and it is going to return 42 plus 78. I think that would be 120 or something like that. All right, so the result is what we would expect in the console. So an object is a special concept in Kotlin in which we define the type and the only possible instance of that type, which we can refer to it directly. Now, a special concept, or a special, let's say, extension to that concept, is that of a companion, in which we add an object inside a class with the same name. So here, under the open class pet, I'm going to add what is called a companion object, and IntelliJ is quick to suggest that for me. So companion object, and inside the curly braces, I will define properties and methods of the pet type, not pet instances. For example, I can define things that the sort, let's call this human love guaranteed, which I assume this is true for all pets. So human love guaranteed is a property of the pet type, not of a particular pet instance. So here under main, I can say print line pet dot human love guaranteed, and this is a property of the pet type. This belongs to the companion object. So property of the pet type, and that belongs to the companion object. Now, in companion objects, we put in properties or methods that we call the static. So these are static properties and methods. In other languages, the concept of static is embedded in the language under a keyword. For example, in Java, we say that the human love guaranteed is a Boolean inside the pet class, and that is static. So this companion object structure is equivalent in Java to say static Boolean human love guaranteed is equal to true. Personally, I prefer the organization in companion objects because every single thing inside the companion object scope is known to be static, whereas in Java you have to pay careful attention to the presence of the static keyword next to every single definition. Okay, the next concept in OOP, specific to Kotlin, is that of data classes. Now, the concept of data classes has some equivalents in other languages. For example, in Java, we have records, and in Scala, we have case classes. In fact, Scala case classes inspired both data classes in Kotlin and Java records. So Scala is kind of the mother of this sort of concept. And in Kotlin, we have a data class. Let's call this person. I'm going to define a val name as a string and a val age as an int. How is a data class different? A data class describes a lightweight data structure. So for example, if you are writing an application that deals with persons a lot, so if you're storing persons in collections, if you're passing them around as arguments and things of that sort, it's useful to make this sort of bag of data a data class. So this is the choice for storing information as classes without necessarily too much behavior. So this is meant to be passed around as a single storage of data and stored, for example, in collections. Now, data classes in Kotlin will make the compiler generate a bunch of niceties for us. For example, the compiler automatically generates the methods equals, hashcode, and toString, which for those of you coming from a JVM background, for example, in Java, you know that all of these methods are very, very important. The IDE can generate them automatically for you, but in the case of a data class, the compiler will generate these automatically for you without any intervention on your part. Equals and hashcode are particularly important because if you're storing these in collections, the ability to tell whether two instances of person are the same is made or should be made out of the data, or rather out of the properties of the data class, and equals and hashcode are automatically generated for you by the compiler to take care of that sort of equality. And toString is a nice human readable representation of your data classes because otherwise classes in Kotlin and in general on the JVM look very weird when printed out to the console. Now, besides equals, hashcode, toString, we have some additional niceties. For example, copy. And this is particularly useful if a data class has lots of parameters and you want to copy an instance where you want to change just one. So copy is very useful. Also, we have destructuring. And this allows for the Python-like decomposition of a person instance. Let me show an example real quick. So let me define a val called Bob as person with the name Bob and age, 32 or something like that. So this is an instance of person. So if somebody gives you, if you don't know how this thing was constructed and you want to access Bob's name and age without saying val Bob name is equal to Bob.name, val Bob age is equal to Bob.age, and so on and so forth for all the 60 parameters of the data class, instead of doing that, instead of writing 60 lines, you can define them in one definition, so we can say name and age is equal to Bob. So this is very Python-like. And this is only possible because we have some destructuring mechanism, and in my Kotlin Essentials course, I talk at length about how this destructuring is made available. If this thing were not a data class, then this sort of deconstruction would not be available. So this is only made available for a data class, as well as the other niceties that we've been discussing. So data classes are very useful if you are storing various groups of data under a single concept, in this case of a person. Okay. Now, the next notion that I want to talk about in this object-oriented chapter is exceptions. And the concept of the crash of a Kotlin application is very similar to other languages, for example, in Java and Scala, not least because Kotlin also runs on the JVM. So we have the same concept there. So let me define a little expression that may throw or catch exceptions. So let me define a val. Let's call this maybe failure. And the structure here is a try catch, so try with some curly braces. You've probably seen this before. And here inside the try, we have some code that can crash. And the crash, in technical sense, on the JVM is called throwing an exception. So, for example, let me define a string called Kotlin. And let's assume that I want to take a substring and I want to return. So string, let's call this language, and language.substring from 10 to 20 without taking care of checking index out of bounds. So this will crash. That is because the indices 10 to 20 are outside the length of Kotlin, which obviously has fewer characters. So this is going to crash. And in order for us to defend against this sort of crashes would be to catch exceptions. So we say catch, and inside parentheses we say e of type exception, and then open some curly braces. And finally, we would return, I don't know, some other string, so some faulty error message. And this is a proper string that is going to be returned and assigned to this maybe failure val if the code inside the try scope crashes. And then you can also add a finally keyword, which here we can execute some code no matter what. And this structure is very similar to other languages, including Java, Scala, C#, Python, TypeScript, with minor modifications just syntactically. Which is why I'm not going to spend too much time talking about exceptions. If you've seen exceptions before in your language, they work very similarly in Kotlin as well. It's just the structure of try-catch, and otherwise you're good to go. And one final thing is generics. Generics is a big concept in Kotlin. I'm just going to scratch the surface here. So generics are very similar to other languages. For example, in Java, Scala, and C#, and also TypeScript, mostly. So generics will follow a very similar concept in these languages. In C++, the templating style is a little bit different. So generics allow for the reusability of code for potentially unrelated types. For example, let me define an interface. And I'm going to define an interface of a data structure that has the same logic, essentially, regardless of the kind of data that it stores. For example, if I define an interface for a list, a linked list, let's call this my linked list. Now, the notion of a linked list is the same regardless of whether this linked list stores numbers or persons or pets or strings. The logic should be the same. So, in order to also enforce that this linked list only stores elements of a single type, we say that this my linked list is typed with a type parameter. Let's call this T. The syntax is very similar to Java, C#, and TypeScript. In Scala, we have square brackets instead of angular brackets. That's the only syntactic difference. And once you define the type parameter T here, then you can use this type parameter T inside the body of my linked list. So can use the type T inside the definitions of the methods or properties. For example, the main API, or the fundamental set of methods that a myLinkedList should expose, is a function that returns the first element. So let's call this first element. And this returns an element of type T, whichever the type of data that this list contains, that's going to be the type of the value that I'm going to return as the first element. And a fun rest or tail, the first method is also called head, and the rest of this list is called tail. So that is all the elements without the first element is going to return a myLinkedList of T. So once you add the type parameter T next to a class or an interface, you can use that type parameter inside the definitions of the methods or properties in question. Okay. Now, if you want to use generics on real collections in Kotlin, for example, actual lists, let's call this numbers, as a list of integers, so you have a list typed with the type argument int, then the compiler knows that all methods of this numbers list are going to return only integers or things related to integers. For example, I'm going to say list of 1, 2, 3, and once you define that this list is a list of integers, the compiler will run a type check on the expression on the right-hand side. So for example, if this list contains other than strings, for example, Kotlin is cool, then the compiler will not compile this code because these are strings, whereas you define the numbers as a list of integers. So the types do not match, and therefore the compiler will not compile your code. This is a very, very powerful feature because otherwise, by having a mismatched type, you can run into very nasty bugs, which is often the case in weakly typed languages like JavaScript and Python. So the Kotlin compiler can check types for us, and that is very, very cool. Not only that, but once you define a numbers list in this case, you can use its methods. For example, first as number 0 with this syntax, with the indexing syntax C style. And we know for the fact that because numbers is a list of integers, then this number is also going to be an integer. That is because the list type is typed with a type argument, and when you index an element, it's going to return that exact type with which you typed the original list. So with a strong type system like Kotlin, once we use generics, we can then make assumptions about the types of the stuff. For example, if I define some strings, so let's call this strings, as list of, we have Kotlin and then rocks, and I'm going to have my first string length. I can say strings at index 0, which is known to be a string, and because it's known to be a string, I can very safely call the length property on that string. If string 0 was an integer, then I could not call its length method. So we know at compile time that my ability to call length is correct. So there you have it, folks, the major object-oriented features of the Kotlin language. Join me in the next part.